acceleration mechanisms. After that, we have a number of people, approximately 8, who've asked for some time to talk on topics related to that, topics on generally in the area of coupling of both hot and cold plasma between the magnetosphere and the ionosphere. We have so many people who've asked for time, I ask each of them to take no more than 5 minutes. A strict 5-minute time limit will be enforced because I know other people may also want to enter the discussion in this area. After 1 hour and a half is up, we'll proceed to the second invited talk by George Reed, and he's talking mainly about the effects of time-varying convection electric fields in the magnetosphere and the ionosphere. We have several people, approximately 4 or 5, who want to make comments on related areas such as substorms, such as any large-scale plasma effects in the magnetosphere. So that gives you an overview. If you have a comment, for example, to make that has to do with large-scale plasma effects, it would be best to hold that until after George's talk. We won't have a coffee break, and at this time, Ferd, you ready?
What I'd like to do is to very briefly review some of the observations of auroral arcs, which is certainly one of the most dramatic manifestations of the coupling between the ionosphere and the magnetosphere, and then go through a very brief discussion of some of the theoretical ideas that have been proposed, but by no means all. And the couple that I have left out, I've done it on purpose because the authors are in the audience and will be glad to fill me in on my transgressions. So if I could have the first slide. It's just a theorist's schematic of the various kinds of auroral arcs or arc formations that occur, just to orient people. Starting on the day side, of course, we have polar cusp aurora, the diffuse auroral light excited by the direct penetration of magnetosheath or... Yeah. Is that up? I guess that's up to me. Yeah. Polar cusp arcs. One also have polar cap arcs, which occur during reasonably quiet times, and about which I don't think very much is really known. The type of arc that will be mostly discussed in this talk might be called the discrete auroral arc, or the inverted V arc, which occurs sort of on the boundary between polar cap or open tail field lines and closed field lines. So one possible, or theorist interpretation anyways, is this line here would represent the last closed line of force in the tail, which would go into the tail, and hence the arcs would essentially map into the tail reconnection region. Other kinds of auroral arcs are arcs, some discrete auroral forms which might appear well within the auroral oval and exhibit properties of strong conjugacy. And at the equatorward edge of the oval, one has hydrogen arcs, mostly H-beta emissions. Now, as a general statement, arcs seem to like to occur on discontinuities of magnetospheric structure. The day side, one has, of course, the discontinuities of the polar cusp associated with the magnetopause boundary, inverted V arcs with the reconnection regions in the tail, and arcs which might occur in the equatorward edge of the auroral oval corresponding to the discontinuity of particle energy in the magnetosphere at the inner edge of the electron plasma sheet. Now,
quite often there are multiple inverted V's. What do you do then about the discontinuity between open and closed field lines?
there may be discontinuously connected field lines in the tail. Very likely. Okay, what I'd like to do is run very quickly through the observations. Most of these are reasonably familiar, and there's been a multiplicity of satellites, rockets, and whatever that have elucidated their properties, and I'll by no means do justice to everyone who's made such measurements, but I think I'll try to hit most of the major features. One of the new research tools on auroras that, of course, has come out have been the ability to look down on a sizable piece of the auroral oval and photograph the large-scale structure of the arcs. This is a shot taken from a DAP photograph and shows sort of the two and perhaps three distinct types of aurora. This is what I would call a discrete auroral arc, which corresponds, as we'll show in a minute, to the inverted V regions. Over on the right, this is sort of an incipient substorm, is a diffuse auroral emission, somewhat less structured, often totally unstructured precipitation that comes in. And this blob of light here is an incipient westward surge. Now, the discrete aurora, which will constitute most of my discussion, because that's one that's been theoretically thought about the most, can occur with geomagnetic latitudes at quiet times up around 70, 71, 72 degrees, getting down to 65 degrees during substorms or just pre-substorm time. So that's a fair range of variability. But it's basically a single arc, or if there are multiple, so occasionally you can resolve multiple arcs. Now, the types of precipitation that create the discrete aurora have been known, of course, since the first rocket shot by Carl McElwain back in 1960. That is, they're electrons with energies the order of 1 to 10 kilovolts. And this, of course, is a color spectrogram of energy versus essentially latitude with color coding on the flux from Ackerson and Frank. This is the polar cap. Very little precipitation at high energies, although that, again, is not always the case. But a sharp turn-on of precipitation on what we would like to call the last closed field line. This structure, this red structure, is called an inverted V or inverted lambda, or a lambda structure, depending on which group you come from. Doesn't much matter. The physics is the same. Basically, it says it comes from the hardening of the energy spectrum, the intensification of the fluxes in the kilovolt range, and drop on the other side. This structure corresponds to the visual discrete auroral arc. There may be multiple inverted V's. Some of them are detached. That is, you could find cases where an inverted V is here, another one here, and another one equatorward, indicating probably that the magnetic field topology that connects into the tail is a reasonably complex thing. Now, another feature in most of these spectrograms is the rather diffuse, somewhat less structured precipitation that occurs on the equatorward edge of the auroral oval, sort of a rise in intensity of precipitation, and then a rather precipitous drop corresponding to the inner edge of the electron plasma sheet. That's even better. So now there's been a lot of rocket shots, satellites, whatever, all trying to measure the spectrum of the auroral particles. And they've all more or less come up with roughly the same kind of picture. That is, it varies all over the place. Typical spectrum is shown up here from a rocket shot. And you can see the well-defined peak in the electron energy spectrum of about a couple of kilovolts energies. If they had detectors to lower energies, this spectrum would have turned around and gone back up again as you got into the low energy, or what might be called the secondary electrons part of the spectrum. But in this, the reason for showing this slide is that they had pretty good pitch angle resolution in this rocket. And you can see that this beam of electrons at 2 kilovolts energy is strongly field aligned. That is, it is a field aligned beam which essentially is just coming right straight down the field line and making the auroral light as shown by a photometer below the rocket. On the other hand, here's a nice energy spectrum, very sharply peaked out right around about 6 or 7 kilovolts, even sharper than that. Pitch angle distribution roughly isotropic. So one can see lots of different things. And it's been my impression from talking with people, although I haven't seen anybody really pin this down, and one thing that some people might like to comment on, that in most cases the most poleward inverted V or arc has a field-aligned pitch angle distribution associated with it. More equatorward ones can often show isotropic distributions. Perhaps that's something we can pass on and discuss later on. Now, I'd like to, you see most people will comment that the energy of electrons in the auroral arcs are the order of 1 to 10 kilovolts. Next is a rocket shot taken from a paper by Baring, Kelly, and Moser. Here again is the electron flux. They flew through 2 arcs, or essentially a folded arc, one here and one here. And what is surprising about the data is that the arc is best defined and most sharply delineated in the flux of particles greater than 15 and greater than 30 kilovolts. You can see that this detector is essentially saturated up here. Tremendous flux. and that the arc is actually best defined spatially, the rocket shot, in the highest energy channels. And so the auroral particles just don't involve beams of 1 to 10 kilovolt particles. They involve precipitation which can extend up to much higher energies, which I think is something that theorists haven't really taken into account and considered very significantly. Now, the next topic I'd like to talk about is the electric field measurements. Here's some. They had electric field detectors on this rocket, but the orientation of the aurora wasn't quite right in order to make a clean interpretation of that. So I'll show another picture taken from a paper by Gurnett and Frank from using Engine 5 data. Here again is the inverted V precipitation, presumably the discrete aurora, plasma sheet. And then here's the electric field measurements. And you can see on the poleward edge of the arc, northern hemisphere, the electric field points southward. Equatorward edge of the arc, the electric field points northward. That is, it is as if the arc structure were negatively charged, and the electric field is pointing in on both sides of the arc. This seems to be a pretty persistent feature of most of the electric field data. Of course, things can get complicated. It doesn't always look like this. The orientations are complex. But most situations seem to show very sharp electric field changes in the direction of such that it will point into the arc. Also note that as you approach the equatorward edge of the oval and you see the fall off in the plasma sheet precipitation, a southward directed electric field is again observed there. And this is of course the cleanest pass that I was able to find and which illustrated that point, but I'm not sure just how general it is. Now, from theoretical considerations, people had speculated for a long time that auroral arcs carry currents. And this was established by rocket shots in the late 60s and early 70s, primarily by Cloutier at Rice. Did a lot of work, and now a lot of others have seen the same thing. And the basic picture that emerges is the following current configuration. This is the poleward edge of the arc, equatorward edge. And this is the total current per square meter of the precipitating electron flux in the energy range of 0.5 to 20 kilovolts. You can see that here would be the precipitation. This would be the location of the visual or discrete auroral arc. There is magnetometer measurements indicate that there is a strong upward field-aligned current in the arc at this point. And over here, there's a strong downward field-aligned current. In addition, of course, electrojet currents on either side. Now, as was mentioned this morning, if you look at the total current flowing in this circuit, the precipitating particles, precipitating electrons in this energy range constitute something the order of 0.2 or 20% of the total current that's flowing in this coax system. The other 80% must be carried by particles that weren't measured in this case, and as we saw in several discussions this morning, even when a wider range of energies considered as often, a net increment of current which cannot be accounted for. So not all the current carriers associated with arcs and field-aligned currents in general have yet to be identified, have been identified at this point. I'd now like to turn to the plasma turbulence, which is associated with arcs, and I'm particularly going to just focus on those branches of plasma turbulence that we think, for theoretical reasons, have to do with the flow of field-aligned currents. On the same rocket shot from Baring and Moser and Kelly, they also had an AC electric field sensitivity. And this is a spectrum which was taken just as they entered the arc for the first time. You can see there's a sharp peak in the electric field spectrum, somewhere between 30 and 50 hertz, which corresponds roughly to the local oxygen cyclotron frequency. And the authors speculated that this is evidence for the excitation of the electrostatic ion cyclotron instability, which had been predicted theoretically by Kendall and Kennel some years ago. And at the same time, or very closely near to this, they measured a strong field-aligned flow of heated ionospheric ions. And they argued that this was essentially confirmed the theory, nonlinear theory of the electrostatic ion cyclotron instability proposed by Palma-Desso and his colleagues at NRL, that instability ought to heat low energy ions, and they ought to essentially expand thermally along the magnetic field and saturate out the instability by essentially heating process. Maybe Dennis would like to comment more on that later on. Another type of emission that's seen in aurora, and also seen essentially all around the polar cap, is VLF auroral hiss. This is a slide taken from Gurnett and Frank again, engine 5 measurements. These are the electron measurements on the night side, inverted V regions, day side, sort of just ordinary polar cuspide precipitation. On the top, you see the 7 kilohertz channel up and all the way up to 70 kilohertz. Strong excitation of low frequency, or reasonably low frequency waves. Waves are primarily electrostatic. The spectrum generally peaks at the lower hybrid frequency, at the lower hybrid frequency corresponding to the altitude of the satellite, but extends all the way up to 100 kilohertz and perhaps even merging beyond with higher frequency noise spectra. If you go a little bit farther out in the magnetosphere, we come to a region which has been very ill explored and will probably remain so until, if and until and when the Electrodynamic Explorer mission gets off the ground. That is figuring out, following the flow of field line currents further out into the magnetosphere. This is a slide taken from the OGO 5 data by Scarf and the usual collage of colleagues that write all the OGO 5 papers. OGO 5 was in the morning sector, about an Earth radius or so above the Earth, on the L equals 5.5 field line. And they detected magnetic field line currents by the azimuthal deviations in the magnetic field. And associated with these field line currents was the low-frequency electric field noise, with amplitudes that got up to 10 to even 100 millivolts per meter, very intense electrostatic waves. These wave intensities are about a factor of 10 larger than you see inside the Earth's bow shock. If you looked at the frequencies and tried to estimate what the plasma was doing, it turns out that these wave frequencies are very close to the local ion plasma frequency, although determination of that is not completely clean, and suggests that the currents that are flowing there are destabilizing ion acoustic waves, or perhaps even if they're strong enough, the Bunneman instability, and producing strong electrostatic noise along these field lines. Finally, there, of course, is the dramatic rediscovery by Don Gurnett of kilometric radiation, which was alluded to this morning. Here's a spectrum taken from one of Gurnett's papers. Auroral kilometric radiation peaks somewhere between 100 and a megahertz in frequency, various other types of radiation that you detect. Has peak powers the order of 10 to the minus 15 to 10 to the minus 14 watts per meter squared per hertz. At those types of power levels, the total amount of radiation emitted by a hemisphere would correspond to something like 10 to the 9th watts. And 10 to the 9th watts is just about what the average decametric radiation is from Jupiter, which is, of course, the EO-modulated radiation, and it puts the Earth in roughly the same power class as Jupiter, as a radio emitter. This radiation, kilometric radiation, is well correlated with the occurrence of aurora. Here, Gurnett looked at various passes of the DAPS satellite and compared them with observations of kilometric noise up on top. You can see here's a pass from the DAP where there's virtually no aurora in the field of view, no kilometric radiation. Next pass, intense aurora, kilometric radiation at a fairly high level. And so the conclusion seems inescapable. The kilometric radiation comes from the aurora. And it must, in fact, at those power levels, come from the precipitating auroral electron beams. The total power from kilometric radiation corresponds to about 1% of the total power flux associated with the auroral electron beams. And those are the largest source of non-thermal plasma energy that really is available in this region of space. By triangulation techniques using the Explorer and Hawkeye 1, Gurnett was able to place the source region for the kilometric radiation at about 1 to 1.5 Earth radii out along the magnetic field lines. Now, sort of in summary then, the discrete aurora tend to occur near places where the magnetosphere has discontinuities in its hydromagnetic structure. The inverted V's represent field-aligned beams at times with total intensity from 1 to 250 ergs per centimeter squared per second. Associated with the arcs are electric fields. Can everybody hear me? This is going to turn this thing off. Associated with the arcs are electric fields which point into the arc and such that the arc looks negatively charged. Finally, there are various types of plasma turbulence associated with the arcs. Now, I'd like to turn to some theoretical considerations, what people think about the basic structure of arcs, and then separate the topic into two parts. One is sort of the gross electrodynamics, the currents in the electric fields that you measure around arcs, and the other is the physics of the auroral electron beams themselves. The next slide is sort of a confection which we put together some years ago and was designed to explain the sort of gross current electric field configuration of the entire auroral oval. But I think the basic physics still applies to the, well, I'll show you will apply to the auroral arcs, and so I'll go over it in some detail. We've seen that the plasma sheet precipitation is essentially spatially inhomogeneous as it comes down and precipitates in the ionosphere. It starts out rather low, peaks somewhere in the middle, and then has a very sharp equatorial boundary. What this means is that the plasma density of the ionosphere, which that precipitation makes, also has a spatially inhomogeneous structure. Now at midnight, where this slide was drawn and intended to be, there is in general a westward electric field coming out at you, which drives a poleward Hall current. But because of the inhomogeneity of the electron density in the ionosphere, the Hall conductivity is inhomogeneous, and there is a divergence in that Hall current. Now, as long as the field lines threading this region and coupling out to the magnetosphere are reasonably good conductors, you can close that Hall current by a field-aligned current in at the equator edge of the oval, goes across as a Hall current, back out again, the poleward edge. How it closes out here in the magnetosphere is anybody's guess at this time. It remains an unsolved problem. Now, as the magnetosphere becomes more disturbed, you have substorms or whatever, electric fields go up, precipitation goes up, and these field-aligned currents increase. Eventually, they become strong enough to exceed the threshold for various modes of plasma turbulence that might be excited along the field lines. And you get, basically, from that turbulence, an anomalous resistance to the flow of current. Those currents can no longer flow completely freely. Okay, can no longer flow freely, and it requires a parallel electric field to essentially drive the current through. And in this particular case, the basic driving electric field was in the east-west direction, or in the y direction, and the EX field is the polarization electric field in the previous slide. And you can see that that polarization field essentially points into the field line current making up the arc. That is, essentially it points southward on the northern edge of the arc, northward on the southern edge of the arc. So I'd like to claim, maybe debated, that the basic electrodynamic structure of how the ionosphere responds to an arc is essentially fairly well worked out. Lots of details, of course, need to be filled in, but basic physics, I think, are pretty much contained in these calculations that Feder has done. Now I'd like to turn to the question which I think is more fundamental, and that is, what is the origin of the auroral electron beam that makes the inverted V's and makes the visible light? Now we've seen that one consequence or one necessity for just explaining things like the polarization electric fields that are observed in arcs is a field-aligned potential drop. So one question you can ask immediately is, can you explain the existence of the auroral beams by having a field-aligned potential? And this problem was worked out and analyzed by Dave Evans, who did the following. He assumed that at engine altitudes, 250 kilometers, he took a non-drifting Maxwellian, a certain temperature and density, let it drop through a potential drop of about 400 volts. Then he allowed that beam that was formed by falling through that potential to interact with the ionosphere, produce secondary electrons, and the secondaries are trapped by the mirror magnetic field at low altitudes and by the potential electric field at high altitudes. And once steady state is reached, you then have a spectrum of electrons that would be formed by just a simple potential. The solid curve here is the result of his calculations, and the dotted points are from Ackerson and Frank's engine 5 measurements. And I think the agreement is rather convincing. Parallel electric fields can certainly reproduce the beam part of the auroral measurements and the secondaries that are usually accompanied that. You can see, however, some slight deviation when you start getting up a high energy. These are the above 10 kilovolts, which I indicated before, were also part of the auroral arc precipitation. This might be indicative that the distribution that you started with wasn't exactly Maxwellian, or it might be indicative that some other process is necessary. Now, once you've established that a field-aligned potential drop is sort of necessary to explain the observations, you have to ask the question, where does it come from and how is it supported? I've indicated that anomalous resistance to field-aligned flows of currents is one possibility for establishing the electric field. The theory for that, I would say, is in an extremely primitive state, which means it really hasn't been worked out at all to anybody's satisfaction. There's another possibility which has been discussed for years and proposed by the Swedish group, Alfvén, Feldhammer, and Bloch, and that is potential double layers that might exist along auroral field lines. I'd like to just remind you that what a double layer is a laminar change in the potential. And it is not turbulent. It does not involve turbulent or fluctuating electric fields, but it is simply a static or, at best, a propagating but laminar transition in the potential. To excite a double layer requires an initial electron drift greater than the electron thermal speed. And once that has been exceeded, you can, in fact, have total potential drops across the double layer, which exceed the KTE energy of the electrons by many times. The structure of double layers is that the total spatial extent tends to be something like 10 to bilengths. And this is a picture that I took from a paper by Bloch, indicating how you might explain the auroral observations by a single double layer. These are the equipotential contours. And if we concentrate for a minute on the center of the double layer, electrons would be accelerated through this in the center, cross the largest number of equipotentials, and reach the highest energy. That's flux. They would be electrons which would appear on an energy spectrum right here. On either side, the electrons cross fewer equipotentials, gain less energy, and the energy would fall off. Flux energy would fall off either side. That is, it's very easy to reproduce an inverted V by having a single double. Notice that the electric fields on the edges point inward. The double layer appears negatively charged. Again, in agreement with the basic observations of auroral arcs. Now, I'd like to sort of make a few remarks about double layers of this kind. First of all, there is absolutely no doubt that they exist. And at UCLA, one of our postdocs has produced them in the laboratory. They're stable. They occur in the laboratory device whenever the plasma density is sufficiently low that the Debye length is a sizable fraction of the system size. Then when you pass an electron current through that plasma, a very weakly ionized plasma, it essentially forms a single double layer. Yeah?
The equipment is not working. This is
that right now? You can try it again.
Try it again.
Okay. Okay, so double layers do exist. What happens in the laboratory, however, is if you put in a little bit more plasma density so that the Debye length becomes then a small fraction of the total size of the system, the same electron current which originally excited double layer breaks out into Bunemann turbulence and ion acoustic turbulence. So one thing about double layers that have always been hard for me, and I'm going to give you now just one man's view of the subject, there are probably many, is that it seems hard to understand how, in the magnetosphere, where the Debye length truly is small compared to everything, you produce this very small double layer potential. And why it should occur somewhere and not others, that is why it should be preferentially always around the last closed field line, etc., I don't know. However, there may, in fact, be a resolution to the whole problem of anomalous resistance in double layers. And that is that there's an analog of double layers in modern plasma turbulence theory. And the argument goes something like this. When you have a beam in a plasma, it naturally produces plasma oscillations. In general, they're rather hard to avoid. And plasma oscillations have the peculiar property that they're unstable to collapse. That is, if you produce plasma oscillations at short wavelengths, those waves couple down and eventually pile up at very long wavelengths. And what happens then is that the long wavelengths constitute a very intense radiation pressure that can interact, it's generally termed the Ponder motive force for those people technical, can interact with the background cold plasma that's there. And essentially that radiation pressure pushes the plasma aside, makes a hole for itself. Now, plasma waves are trapped in regions of low plasma density, and so you have the high-frequency plasma oscillations that are essentially then remain trapped inside of a low-density region, which of course must correspond to a potential. And this whole structure is called a caviton or a spicon, depending on whether you come from UCLA or from Livermore. Doesn't much matter. In any case, it looks a lot like a double-layer structure. So, in fact, the equations look a lot like double-layer structures, except that associated with them, they're not just completely laminar, they involve a lot of high-frequency plasma noise. So one possibility is that the auroral currents, in fact, in beams destabilize such structures. Particles can get accelerated stochastically and laminarly across them, but that they aren't steady. That is, that an auroral arc doesn't consist of a single double layer like this, but a whole random distribution of double layers turning on and off and destroying each other and eventually accelerating up the particles which we see precipitate as the auroral beams. They said that's one man's opinion. Now I'd like to turn to the radiation problem. How can we explain the observed types of plasma radiation that we see coming from the aurora? The first problem, because it's the best in hand, is the problem of VLF auroral hiss. For many years, people thought that auroral hiss, VLF hiss, was simply the summation of the incoherent Cherenkov radiation from the precipitating auroral electrons. But we got interested in that problem, and a postdoctoral fellow of ours by the name of Jim Maggs looked at it and decided that if you looked at the auroral spectra, electron spectra, in phase space rather than in differential energy versus energy, they often find that they have regions of positive slope and velocity space. That is, they ought to be unstable. And so he set up the following code. Took an altitude, let's say corresponding to engine altitudes, and took a spectrum of frequencies at that altitude that would correspond from the lower hybrid frequency up to the plasma frequency or cyclotron frequency of electrons. He assumed that each wave propagated on the resonance cone, which is a good approximation for electrostatic whistlers, and he ray traced it back up the field line to find out where it came from. He, of course, put in a model of an auroral arc, which was spatially limited in the north-south direction, if you will, to the observed height or observed widths, and put in the curvature of the arc, too, because, after all, waves won't remain forever in an arc if it's curved. And he computed out the total power spectrum, that is, a total power amplification over incoherent Cherenkov emission that you ought to see as a function of frequency. And these are the results. Here you plotted power, watts per meter squared per hertz, against frequency. He finds that the spectrum for Hiss peaks near the lower hybrid frequency. In this case, the peak occurred twice the lower hybrid frequency, but where it peaks depends on the parameters of the beam and background density and models and whatever. He has no trouble accounting for the total power. In this case, 10 to the minus 13th. It's very easy to construct beams which will produce 10 to the minus 11th, which is the largest power ever seen in a VLF His burst. And in general, the power spectrum decayed with higher frequencies. Now, he found that if the plasma frequency of the electrons exceeded the cyclotron frequency everywhere along the ray path, in fact, the power spectrum just came down and died at the plasma frequency, or at the cyclotron frequency. If the plasma frequency was less than the cyclotron frequency, then the power began to turn up again and, in fact, became exponentially large, very close to the electron plasma frequency. And this, of course, are simply the plasma waves that are excited by the beam-plasma instability interaction. And since this was a strictly linear convective theory for the wave growth, there's no way of determining at what amplitude those saturated. As far as the rest of the VLF His spectrum is concerned, it is explained simply by linear propagation and linear convective amplification of Whistler waves. Now, at the frequencies at which the theory predicts very large wave growth, those frequencies are also in the kilometric range. And if you look at various models of the ionosphere, frequencies in the kilometric range, let's say 100 kilohertz to a megahertz, occur above the Earth in about a half to 1 or 1.5 Earth radii region along the field line. Exactly the same spatial region which Gurnett triangulation measurements indicated that the radiation had to be coming from. And so it's perhaps no coincidence that the plasma oscillations associated with the beam and the frequencies involved might have something to do with kilometric radiation. Now, I only know of one theory for kilometric radiation, and I'll try to describe it for you, and Dennis in the back of the room could probably do a better job. And the argument goes something like this. If you try to say you take the plasma waves and they somehow mode couple together and eventually find their way out as electromagnetic radiation, you find that you simply cannot reproduce the powers that are seen in kilometric noise by orders of magnitude. And so Palmadesso and company at NRL suggested that the kilometric radiation had to come from some type of plasma instability, and the only possible kinds you can have in order to radiate electromagnetic waves are of the parametric type. And the physics of their process is this. If you assume that in the plasma, the low energy plasma, it carries a large amplitude spectrum of short wavelength but very low frequency ion waves. Now, at those low frequencies, the electrons are essentially coupled right with the ions. You have local charge neutrality. Now, if you take a long wavelength electromagnetic wave and oscillate it back and forth across those ion density fluctuations, the electrons, of course, tend to get pulled away from the ions. But they don't like to do that, so a charge separation electric field builds up, which has the frequency of the natural electromagnetic wave that you're pumping them with. And that is simply an electrostatic wave, a plasma wave, or a Whistler, or something like that. And if the phase velocity of that high-frequency electrostatic wave is resonant with in a region of positive slope of the electron auroral beam, then that plasma wave will grow. It's unstable. But because of the parametric coupling, all the waves that are coupled together are amplified at the same rate, so that you can amplify the electromagnetic waves even though they are not resonant with the auroral beam itself, but resonant only through this parametric coupling. And they estimated the types of ion plasma turbulence that you would need to get reasonable gains. Sort of the results are shown on the next slide. What plotted here is the energy growth length, that is the length that it will take to e-fold the amplitude of the waves once against ratio of plasma frequency to cyclotron frequency for various intensities of the low-frequency ion waves. The basic point is that for most cases, which are not necessarily unreasonable here, growth lengths the order of 100 to 300 kilometers are required. And they estimated that you could get a total gain of roughly a factor of 10 to the 8th in traversing the region in which frequency matching could occur for the parametric instability. Now, as a mechanism, I think this is a very likely candidate that although this particular process may just be representative of a more general class of processes involving parametric couplings, that the problem, I think, are the long growth lengths. We learned from the calculation of the VLF His spectrum that propagation is incredibly important in determining how any instability works in the ionosphere. You simply have to do the convective growth calculation, putting in the wave refraction. Because a wave which starts out resonant with the auroral beam, a few kilometers later may have refracted its wave vector sufficiently far away that it no longer is resonant and is damped. So I think what is required in order to proceed on the kilometric problem is to redo calculations of this type, putting in the wave propagation as an integral part, and then see whether or not you can couple out enough electromagnetic radiation to explain the observations. Well, in summary, have the slide off, please. I'd like to claim that the gross electrodynamic structure of the aurora, the field-aligned currents, the polarization electric fields, and the electrojets associated with them, the physics of that is fairly well understood. But the plasma physics of the auroral beam, what we understand of it, leaves a lot to be desired. As far as where the beam comes from, we talked about anomalous resistance, unworked out theory, double layers, laminar, or perhaps a version of the spike-ons or stochastic double layer formation. Recently, Lou Frank at Iowa has suggested that double layers represent the accelerated debris of the reconnection process. That the beams represent the accelerated debris of the reconnection process directly. And it doesn't need any additional acceleration to occur along the field lines. It's a possibility. We don't really know quite yet how to evaluate it. Of the radiation problems associated with arcs, I think the VLF His problem is fairly well understood, at least the physics of it. The kilometric noise remains a rather difficult problem. It's a pretty tough nut, the kilometric problem, because the beam of auroral electrons must produce 1% of it, take 1% of its energy and couple it into escaping electromagnetic radiation. And yet that radiation cannot destroy the beam, because these beams are seen over altitudes of several thousand kilometers. They obviously go a long way without being destroyed by any nonlinear processes that would tend to flatten them out. And so the turbulence level associated with the kilometric problem must be very finely tuned. It must have just enough turbulence to make the observed radiation, not enough to wipe out the beam. Now, this whole problem of field-aligned beams and their radiation is, of course, not just limited to the Earth. There are now 4 well-known and 1 less well-known object in the solar system which emits electromagnetic radiation by probably essentially the same process. They are, of course, the type 3 radio bursts from the Sun, decametric radiation from Jupiter, hectometric radiation from Saturn, and Brown has now recently, rumors have it, has seen 500 kilohertz radiation from Uranus. All of these spectra have a fairly broad range in frequencies, which indicate that the beams of particles that are making the radiation must have traversed a fairly large distance to have passed through a sufficient range of plasma parameters to account for the excitation of all the frequencies. So these beams must persist for a long time. And in particular, the case of the type 3 radio bursts, they've been seen all the way from the solar corona out to and past 1 AU. So solving the kilometric problem is, I think, one of very general significance for plasma physics in the solar system. And of course, one needn't stop there. Electromagnetic radiation processes exist throughout all of astrophysics, and we certainly expect from our experience with the Earth that field-aligned currents should also exist in many astrophysical objects. Those field-aligned currents may well take part in much of the radiation that we see from astrophysical objects. I think, however, that theory alone will not provide the complete answer to the kilometric problem. It's going to be necessary to go out, make observations in the generation region, with an in-situ spacecraft. And I think, therefore, most theorists are looking rather forward to the Electrodynamics Explorer mission, which hopefully will fly right through that region with sufficient plasma detectors and wave detectors to tell us really what's going on. Well, with that, I'll stop.
I'd like now to entertain specific comments on Ferd's talk for a while. I think Dr. Hofstadel had his hand up first.
basically two comments. One is related with field-aligned electron problem. The other one related with this VLS, I mean the kilometric radiation problem. For the first subject, you have mentioned the anomalous resistivity and the double layer formation as a possibility for the parallel or field-aligned electric field origin. I have recently done a theory that entirely another possibility that create field-aligned electric field. I don't know if you knew it or not, or knowing ignored it or not, I don't know, but I think I have told you some time ago informally. It's not published, and that is basically the electric field due to the fact what I call the finite ion gyre radius effect. In other words, if the magnetic field moves, if dB/dt exists, and that certainly can generate electric field, but usually people think that generate electric field perpendicular to the magnetic field. But if the scale size is on the order of ion gyre radius, electrons and ion cannot drift at the same rate, because obviously the gradient B, or whatever the drift, E cross B drift, is different between electrons and ions if the scaling is in the ion gyre radius, and therefore you can set up the fairly large electric field within the disk, which has a variation perpendicular to the magnetic field on the order of ion gyre radius, but also it can produce field-aligned electric field. And one interesting aspect of that generation mechanism is that that kind of electric field would exist only within a thickness perpendicular to the magnetic field on the order of ion gyre radius in equator. And if you project it down to the Earth, it comes typically on the order of 10 kilometers, which is usually the thickness of the discrete aurora. And therefore, it's very encouraging to me compared with this anomalous resistivity concept, because anomalous resistivity has a scaling typically on the order of several dB lengths, and also the time scale of 1/ion plasma frequency, which is sort of sporadically distributed irregularly, and therefore it's difficult to maintain in a large scale expanded on the order of 10 kilometers thickness, but a few hundred kilometers in the east-west direction. And in that respect, I think this should be considered to be an interesting new alternative. As for the emission, there are another way of radiation, creating radiation at kilometric range, in addition to what was introduced. And that is, what you need is that presumably you would have a fairly large electrostatic turbulence created by electron beam. And so what you need is a method of conversion of electrostatic wave to electromagnetic wave. And one could do that by decaying into Whistlers, from plasma frequency to Whistlers, or by linear mode conversion through non-uniformity again. But probably decay to the Whistler is more likely to occur. That is another possibility that I think you can explain.
I think the trouble with that is, if you look at the you ask the question, even after the decay, can the radiation get out? And it's rather difficult. It has to go through several tunneling regions and conversion regions.
No, if the Whistler is generated right at the top side of the ionosphere, it can go out through the ionosphere.
No, Dennis is shaking his head, and I think I agree with him. You have to really look at the right ray tracing.
Is that right?
It won't
Okay,
work.
I withdraw this comment.
It won't work. Your other comment, however, is interesting, and it may be that that's the source of discrete aurora, which you might see on what are clearly conjugate, called conjugate aurora.
In fact, it may be related with this debris idea that who mentioned this? The debris of the tearing mode, or the reconnection effect.
Oh, Franks.
Yeah, Franks. In fact, it can be coupled to this dB/dt occurs at the merging point, and then that dB/dt converted into the electric field and the magnetic field.
Yeah, in that case, I guess what you would expect is that the auroral beam would be formed essentially out in the tail,
and come down.
And then just come down. Yeah, I think that's a very good possibility.
next?
Well, I think I would tend to disagree with the first part of your conclusion that we understand reasonably well the gross electrodynamics of the arcs. And I think that impression basically comes from the fact that you have taken several plausible ideas and treated them as established facts. In particular, I really wonder how firm is the evidence for the statement that the arcs are associated with discontinuities in magnetic field topology or structure. No, it is not enough to say that they occur near the last closed field line. Everything in our roll zone is near the last closed field line on a gross scale. To make a significant statement, the nearness has to be on a scale comparable to the arc thickness itself, and I think that's rather hard to establish. And notice you sort of rely on a circular argument, and when it's pointed out that there are, in fact, multiple arcs, then you say, well, there must be multiple changes in topology, for which I think there is no real direct evidence, although certainly not impossible. And also, I'm not really aware that there's any clear evidence for the existence of two types of arcs, the inverted V arcs and the conjugate electron arcs. I think they're a theorized construction which is reasonable, but again, I am not aware of any experimental evidence that such things exist. So I think all of these questions remain rather unsettled. And the basic assumption in this whole question of the arc theory, and any statement, so the academics is understood, presupposes that the arc is basically a magnetospheric effect, which is modified by the ionosphere, but is not directly produced by it in any way. One simply has a current coming down from the ionosphere for some unknown reason we speculate about, and as a result of anomalies, David double layers or whatever, creates a particle beam. But if the arcs, in fact, are not associated always with discontinuities in external field or external current sources, then this interpretation will not hold up. And there is a quite extensive alternate body of theory, of which now the representatives are sitting in the audience, in some cases, which would attribute the deformation of the arc itself to some sort of a direct feedback process from the ionosphere back to magnetosphere, rather than simply a passive response of the ionosphere to a magnetospheric source. And the dynamics of such systems, I think, are very poorly understood. And my final comment on this connection, I think it's highly important for this purpose for the experimentalists to finally agree on what the thickness of an arc is. The inverted V's is 100 kilometers, and some of the rocket flights show tens, hundreds of kilometers, and as Gavak just mentioned, 10 kilometers is a good number. No, the optical people like Akasova have been telling me that the arc is in fact something like a fraction of a kilometer, and the apparent thickness is due as a projection effect, which is the sheet along the field line. So I think we need putting aside all theoretical speculations, some clear agreement from observations as to what is the real thickness of the precipitation and of the visual emissions, which need not necessarily be the same.
That's okay. I accomplished my mission.
Well, actually, my comments were very much in line with Vytenis, and I would just ask, how do you know where the last closed field line is? What observational evidence are you basing this on?
I'm not basing it on anything. I'm saying that if you look at the auroral oval and you look before you see the inverted V and you look in the polar cap, there's not much precipitation. It's a likely interpretation that's very near the last closed field line. Okay.
Well, I think I would echo what Vytenis said, that you must be more careful about what you say.
I am not the one who's always saying these things. This is
Third, I have a question with respect to the VLF His, essentially. You feel that the theory is in good shape by doing a convective theory, but there is one other point, that when you create these waves at the plasma frequency cosine theta, where cosine theta is the angle between the magnetic field and the wave vector, if you look at the group velocity of these waves, falls exactly on the ion distribution, which means that you can have a very strong nonlinear Landau damping. And since the lowest allowed frequency is the lower hybrid, what can happen is that every high frequency wave you generate turns the K vector and it becomes lower hybrid frequency. And this can explain the VLF His in terms of
you start off with a frequency and it remains a frequency. It may produce other waves. What you're saying is that you may be able to decay some high frequency waves down into the lower hybrid range, so that the
You decay
peak,
all of them,
so that the
collapse
peak,
them.
yeah, so that the peak in the spectrum may occur by other processes.
Did you
Possible.
look at no, so I haven't finished my question that I was trying to explain. Did you look at the wave energy density that's predicted with the convective theory? Is it comparable with what this mode coupling process would do?
I'm not sure that Jim ever looked at that. You couple the electromagnetic wave to the ion density fluctuations and produce an electrostatic wave, which is unstable.
Electromagnetic wave. It doesn't have to be electrostatic. It can be electromagnetic
but
directly.
The theory was done for the electrostatic wave, so let me restrict myself to that. That wave, if there's a positive slope there, that wave was unstable to begin with. And it was also unstable with a growth length that was far less than the several hundred kilometers that you need for the parametric coupling. And so I think there's a serious question, why wasn't the beam destroyed by its natural plasma oscillations that were uncoupled? Now, maybe you can argue that there's enough wave scattering out of the beam to, by essentially, again, going back off the ion fluctuations to do that. But I think the point I was trying to get at is that all of those ideas are very promising. But what they need is detailed path-integrated growth calculations and work in putting in the propagation of the waves in order to establish them.
Yeah, well, I disagree with you that the calculation was electrostatic. It was on the dipole approximation k = 0, which means electrostatic or electromagnetic.
Not for the electrostatic wave that resonated with the beams.
The mode coupling. The mode coupled, namely, I am going to come back and maybe in my allotted 5 minutes, I will discuss the question. I will discuss the question of the stability. No, that's not it.
Maybe we could.
The mode coupling theory that we produced couples the low frequency fluctuations directly to a dipole wave. I mean, we could have done it directly electromagnetically. We sort of took the k = 0 approximation because it was easier mathematically. I agree with you that it needs a lot of elaboration and everything else. I mean, we sort of thought of this idea of having a laser in space that can do that, but I agree that it needs more elaborate calculations, but it is not electrostatic. It's dipole approximation.
No, the wave that escapes, the electromagnetic wave, sure, it's a dipole. But the plasma oscillation that resonates with the beam is not a k = 0 mode in your theory. That's the one I was referring to.
Okay. We'll discuss that. Okay.
I'm always amazed by what seems to be preferential treatment that magnetospheric waves get over ionospheric waves, and in particular the problem of electron transport being reduced presumably by plasma waves in the F region and higher. And I think this is reflected in a slide where you are very happy to show parallel potential drops, but then immediately drop back to what seem to be conventional transport coefficients perpendicular to B in the E region, that is the ordinary Hall and Pedersen conductivity. And yet one knows from a number of radio radar type measurements that in fact the wavelengths of very intense waves in the E region and lower F region are much shorter than the electron mean-free path in those regions. And it seems to me that it should be a legitimate concern to worry about transport in those regions as well as the higher regions, because it may lead to a number of very interesting consequences.
Yeah, I couldn't agree with you more, and the only reason I didn't talk about them is there wasn't time. But the whole problem of electrojet instabilities and F region instabilities, irregularities, and all the modifications of the transport problem certainly are at the base of this auroral arc and how the currents close, and they have to be included. That's right.
Chairman LaForest?
If we could return for just a moment to the observations and the things that Vytenis was talking about, could you review just briefly any one-to-one correlations between discrete auroral arcs and inverted V's? What evidence is there linking them? I mean, you accepted it as established.
Well, there's at least one paper that did it. And I think that if you look at the television pictures that Cliff Enger has, and you look and you ask, where are the discrete aurora? Okay, they're always at the poleward edge of the oval. You ask, where are the inverted V's? They're always at the poleward region of precipitation. The inverted V's are certainly intense enough to produce a visual aurora, so what do you conclude? I'll leave it at that.
I think we need to limit to one more comment on specifically on Bert's talk.
I don't think I agree with what you just said, Ferd. Incidentally, I thought it was an excellent talk, but I was under the impression, and this is a long time ago, that Ether and Mendy published a paper in which they showed a type of very soft precipitation above the discrete auroral arcs. Now, this precipitation had an average energy for the electrons they inferred from their photometric observations of the order of 0.5 kilovolt. And in fact, if you look at the spectrum and you look at the intensity of the precipitation, it appears that it would be partially equivalent to a partially filled loss cone from the plasma sheet at something like 17 Earth radii. Now, if in fact you interpret their observations to imply that the soft radiation, the soft patchy radiation they saw above the discrete auroral arcs was indeed from the plasma sheet at something like 17 Earth radii, that would contradict your conclusion that the discrete auroral arcs in fact occurred near the last closed field line. And I think you have to go back and look at this.
Let me ask you this. Was it a morning side event or an evening side?
Well, I believe they showed both morning and evening. In fact, in their picture, when they showed the area that they observed, they showed a shaded region which went from all the way from dusk to dawn on the night side. And they showed a region which was something like, I can't remember exactly now, but it was between 5 and 10 degrees in width above the last discrete auroral arc. A region in which they claimed that they observed patchy precipitation of relatively soft particles. And these soft particles, as I say, if you assume that you have a partially filled loss cone from the plasma sheet, I think you needed about 1/5 of the flux for a fully filled loss cone, you could explain this radiation according to their interpretations of their photometric observations. Now that seems to be, it's obviously not any proof, but it's sort of compelling evidence that perhaps there is a plasma sheet that lies beyond or at higher latitudes than the last discrete auroral arc.
Well, I'm not quite sure what to say to that. Walter Hickel, of course, has reported observations of precipitation over the polar caps, with polar rain and squalls and whatever.
That's usually on the day side. That's on the day side, isn't it, Walter?
I don't know.
The
Maybe
polar rain and the polar squalls are on the other side of the cusp. I mean, they're on the high latitude side of the cusp.
Do they extend over the polar cap? Because
Yeah.
Sure.
I'll just very quickly try to review then what we'd see over the polar cap. We always see a very weak rain, and rain we call a polar rain, like magnetosheath flux. We see bursts of electrons coming down, which we think are associated with the sun-aligned arcs. And then during storm times, a very transient phenomenon, we see what we call as squalls, very intense events. We have seen them mostly on the day side of the pole, between the pole and the day side oval. I think from the optical evidence that Cliff Anger has, it looks like they may be perhaps go further toward the night side, but preferentially on the morning side.
Right. You're familiar with Ether and Mendy's paper that I'm referring to of about 5 years ago, aren't you, Walter?
I'm sorry, which paper is that?
Well, it's an Ether and Mendy paper in which they observed the soft radiation above the last discrete auroral arc for about 5 degrees on the night side. It's a photometric, it's from an airplane flight, photometric observations.
That's a sort of flight along the oval.
Flight slightly, yeah, along the poleward side of the oval, that's right.
Well, let me just say that I do agree with Bob Holzer that I think there's lots of evidence that there are particles, essentially plasma sheet, which extends poleward off the discrete arcs. I think it is certainly a mistake to associate with the discrete arcs with the limit of closed field lines.
Well, I think that I made the claim simply primarily to motivate this discussion that has occurred. That was my charter by the chairman, that I had to provoke controversy, so I tried to. And I think this is one of the very serious questions that we really should try to answer. That is the last closed field line a boundary that has any significance in the ionosphere? Does it associate with the arcs? And if so, what kind of arcs? Is it only quiet time arcs maybe occur on the lat? Maybe during disturbed times things are so messed up in the tail, don't know. So I'll leave it to the experimentalists. These are questions which can never be resolved by theory.
Thank you, Bert. We have about a half hour of discussion. We have about a half hour of discussion time now on the general topic of the coupling of plasma, hot and cold, between the ionosphere and magnetosphere. And I'd like to start this. There's a dual presentation by David Winningham and David Evans on low-altitude plasma observations in the cleft. While they're getting organized, I'll just mention there are a couple of presentations on low-altitude plasma observations. There are one or two on theory of arcs and particle acceleration mechanisms. Then we'll go to some high-altitude observations and some ring current type observations.
First of all, since the chairman wouldn't recognize me in the back of the room, I'll take this time to get recognized by default. That the answer that I was going to give as an experimentalist is that the statement that Ferd made is completely erroneous, that things which are called inverted V's, which are really an artifact in reality of the spectrogram presentation, if you want to get right down to the nitty-gritty of it, those things which you see on a spectrogram as a nice little black area going up and down can occur anywhere you want to within the region of particle precipitation, 5 degrees, 10 degrees below the polar boundary. And a polar boundary distinguished away from polar rain, polar squalls, or whatever you want to into that. Okay, if I could have the first slide. The results I'm going to present are particle results from a rocket flown by the Los Alamos Scientific Laboratory, which included a shape charge barium release. And the goal was to launch this just inside the, just poleward of the cleft equatorward boundary to investigate the plasma convection in the cleft. There were 2 shots, of which this is the second result. The particle spectrometer is included as an environmental monitor to be able to give a reference frame within which the cloud was injected. The spectrogram presentation you see is the same one that's been used by various experimenters, including ourselves. The altitude scale is here 1, 2, 3, 4, 5, 600 kilometers, an apogee of roughly 540 kilometers. The rest of the presentation is essentially standard with the satellite results. The only difference being that one spectrum is taking roughly every 1.5 kilometers, which is a good bit better than the measures that have been made on satellites. The other difference is the spectrometer was mounted at 45 degrees to the rocket axes, and the vehicle is stabilized relative to the magnetic field line by an active stabilization reaction jet system. As the rocket climbed, you see a region of atmospheric photoelectrons coming from above, because the atmosphere was sunlit both to the visible and ultraviolet. After, Neil, what was the shadow height? About 300 or so kilometers, I believe. Something on that order. So the atmosphere is sunlit to the sufficient extent that atmospheric photoelectrons are being produced above the spacecraft, coming down and being seen. A transition is seen from atmospheric photoelectrons to much higher energy particles. This region and this region have, quote, the type of spectra which we and other people have said, aha, these are magnetosheath electrons. Basically, they're low energy particles with a average energy around 100 eV and a basically Maxwellian spectra. In this case, you can see 2 things which, if you look at it, you'll say, aha, that's an inverted V, because it goes up, down, up basically, steady, and then down. After we analyzed the results, we said, this looks a very good case for parallel electric fields. So I entered a cooperation with Dave Evans and Ted Spicer to analyze this data with the theory that Dave Evans had developed in using his coding, and also with the modifications developed by Ted Spicer. So if I could have the second slide, taking a spectrum right in the peak of the second inverted V, quote unquote. Second slide. This is a observed spectrum here, the dots, the black dots. The open squares and open triangles are two theoretical spectra. You can see the characteristics here of temperature, the acceleration potential, density, and the gradient in the magnetic field, and the pitch angle at which the particles are measured, which in this case was identically 45 degrees. You can see for the case of the triangles, which is the acceleration potential of 800 eV, a temperature of 121 eV, and a density of 1.6 per cc, you get a relatively good match between the measured and the experimental. Dave in the next talk will show later refinements to this theoretical fitting, and actually Ted Speiser has fitted all the spectra for the second inverted V, showing the variation in temperature, density, and acceleration potential, assuming that this is due to an electric field parallel to the magnetic field, accelerating a basically Maxwellian population for the magnetosheath. And Dave will show this next. Excuse me, one other thing I should say, that there were quote-unquote arcs within the region of the spectra that we saw, which you could identify as inverted V. Now you notice I didn't say that there's a one-to-one correspondence, just that within the spatial region we saw them, they occurred together. At the time these spectra were measured, there was nothing measured in the all-sky camera, but before and afterward there were arcs within the general region of this.
David?
I have to use this thing here for me. The scheme here is that Dave sends us energy spectra, and we go and try to match it with this very simple electric field backscatter type model. There's a limited number of parameters that we're at liberty to use. The three most important are the potential drop that we assume to exist along the magnetic field, the number density and the temperature of the reservoir of plasma, which is presumably feeding particles into this acceleration region and then jetting them out at the bottom toward the atmosphere. Ted Speiser has taken a whole series of energy spectra from Dave Winningham during the second inverted V, and independently and individually matched each and every one of these spectra to a model calculation where the potential drop, the number density, and the temperature are parameters. Is it plugged in? Okay. These are the results of them, traced out. The top curve is the temperature of the source plasma, so to speak, the plasma that's above this electric field region and is diffusing across the boundary into the electric field. The center curve is the number density of this plasma, and the bottom curve is the potential drop along the field line that was required to get the best subjective match between a model spectrum and the observed spectrum. I think this is very interesting because unlike most high latitude precipitation patterns, we show two parameters which in fact don't change very much as one flies across this inverted V. The temperature of the source plasma stays at 117 degrees to within less than 25% during this period of over a minute. The number density fluctuates by plus or minus 30%. On the other hand, the potential drop along the field line goes from less than 200 volts to almost 1,000 volts. I really like to stress the importance here that we found two parameters which don't change as you fly across a precipitation region.
Any questions? Okay, next, Vitenis.
Yeah, it strikes me as rather significant that both in this case and in the example showed by Pat Rife this morning, the densities which one infers are quite low compared to what one expects in the magnetosheath. One typically should have something like 10 or 10 to 20 per cubic centimeter almost anywhere in the magnetosheath. I don't know what it means, but I think it's a significant fact.
Next, call on Bob Hoffman for other low altitude plasma observations from AED, I believe. After we talk about theory, then we talk about high altitude observations. Well, the theory people I think who've talked are Lennartson, Papadopoulos. High altitude people, Parks, Johnson. People talking about ring current type things, Garden Shepherd.
We had an array of 19 electrostatic analyzers in AED satellite, some with stepped energy and some with fixed energy at fixed pitch angles. I'd have the first slide, please. So our spectrograms at the top of the one detector measuring essentially field-aligned electrons. This one at about 60-degree pitch angle from 200 eV to 30 kilovolts. During this particular pass, we encountered a series of 4 inverted V events. This is a third one. It lasts about 90 seconds in length of time. The second one, also the fourth one, about the same length of time. The first one was the shortest, it was about 10 seconds. Could we have the front lights off at least? If you look at the spectrograms, you'll see that there's the darker the black, the higher intensities on these. That there's a lining here of maximum intensity at both pitch angles. The difference being at the small pitch angles is considerable intensity at below the peak energy also here. Sometimes the peak energies at the 2 pitch angles are the same, sometimes they're different in both directions. When the peak energy at the 90-degree or 60-degree pitch angle is greater than the peak energy at 0, an interesting thing seems to happen, shown on the next slide. We're just looking now at this particular event, and especially the first part of it. This is showing here the ratio at 0.72 kilovolts of 2 of the fixed energy angle detectors. The kind of base here is the ratio of, is the flux, not the ratio. This is the flux at 60-degree pitch angle. The top stuff that fluctuates is at 0-degree pitch angle. And you'll notice that there seems to be a core of radiation that stays very constant here in the inverted V event at this particular energy, whereas the field-aligned flux fluctuates over about an order of magnitude in intensity, starting as a low intensity at the same flux value of the 60-degree particles, but then goes up about an order of magnitude above it. If the inverted V event is due to acceleration of particles, say like in a double layer, I've heard commented as a fairly stable feature, which one probably would need for the entire event of a minute and a half here, one could not, I think, explain then the high frequency fluctuations, which are several hertz here. There's 16 samples a second taken on the plot there. And it seems to be inconsistent then with that type of an acceleration mechanism for a field-aligned event. Thank you.
Any comments? Okay, if we have no other contributions on low-altitude plasma observations, we'll go to theoretical considerations, and I think Walter Lennartson is the first volunteer.
I would like to comment on parallel electric fields and the concept of parallel conductivity. May I have the first slide, please? This is a purely conceived electric circuit containing a load resistor and a magnetized plasma with straight magnetic field lines. The electrons are provided by an electron emitter, and we have an ion source to the right. In this case, we would, if the plasma is collision-free, we would be able to drive a current through the system with no parallel electric field at all. even if the emitted electrons are energetic and emitted in all directions. If we introduce a magnetic field shaped like this, things are somewhat different. If the ion current is not too large, this region will obviously charge negative because the major portion of the electrons may get mirrored. And we will thus consequently have a parallel electric field in this region, which will increase the flux of electrons relative to the case without electric field, and at the same time the electrons that go through will increase their energy. And this will be true even if the distribution of the energetic electrons are isotropic. It does not at all require any loss cone distribution or anything like that. And the magnetospheric case, I think, is fairly similar. May I have the next slide, please? In the magnetosphere-ionosphere current system, we should find a dynamo somewhere which is equivalent to electric charges moving in the opposite direction to the electric force. And in this case, moving transverse to the magnetic field lines being vertical or fan-shaped like that. And this motion is possible only with energetic or hot electrons and protons, like solar wind particles, for instance. And somewhere along the drift path of these particles, the charges will tend to accumulate, driving a current through the ionosphere. And where the positive space charge appears, it will allow cold ionospheric electrons to escape according to their own thermal motion. And this can produce a very high current density, which presumably will take care of the downward part of the current, field line current. And this will charge the ionosphere positive with respect to the negative terminal of the battery. The escape flux of cold ions may be too low to take care of the upward part of the current, which then consequently will have to be carried by the hot electrons themselves moving downwards. The ambient cold electrons, they will be pushed back towards the ionosphere where they came from, leaving a region with only the hot electrons, that is negative charges, back. And these, of course, they tend to get mirrored. And we will then consequently have a parallel electric field in this region. This region may expand downwards towards the ionosphere, presumably. So, except for, this is a very likely situation, and apart from that, this kind of electric field can also seemingly account for a large number of auroral particle observations, including very different pitch angle distributions varying from field line to loss cone distributions. And needless to say, the particles that go down, that are forced down by the electric field, will have an inverted V distribution, of course, if we go through it. And we may also notice in a simple-minded manner that this is a magnetic bottle confining these hot electrons. And with analogy to the fusion plasma, you would expect this confinement to be only imperfect. So we would expect plasma instabilities that tend to decrease the confinement, which would be equivalent to decreasing the magnetic moment of the electrons. And when doing this, the waves would create bursts of field-aligned electrons, presumably auroral rays, and at the same time it would create kilometric radiation at the electron gyro frequency, for instance, in large amounts. And well, I suppose that's about all. And so my main point is then that even without anomalous resistivity, we would expect parallel electric fields to be a very common phenomenon as soon as there is a buildup of negative charge consisting of hot electrons within a flux tube.
Comments? I think we have 5 minutes now for a combination of Dennis Papadopoulos and Akira Hasegawa. Do you each? Yeah, and then we'll go to George Reed's talk, and then use up the remainder of the time coming back to some of the discussion here.
I had of Akira because I was wasting my last 5 minutes.
No, I think Dennis is first. If you take the whole 5, well then Akira waits till after George Reed.
Being a plasma physicist, the first thing that sort of generally disturbs me is that you have a beam of precipitating electrons and comes down, and it doesn't quasi-linearly stabilize as we all learned in first-year graduate course. And this is, to me, appears sort of a more important physical problem than the acceleration. And then you can come back and see whether the fact that it doesn't stop or it doesn't flatten out might be connected with acceleration. So the whole, if I would have liked to have a few more minutes to sort of discuss some concepts of anomalous resistivity that I believe we understand. So I will stick into one concept that is happening. Here is from some work that I've done with Peter Palmadeso and I've presented before. We have this following situation in the aurora. We have a beam of particles that comes straight through a plasma. And what plasma physics says is that within about 30 kilometers, this should flatten out. People look for that and they don't see it. Why it doesn't happen? So that's the first question. Sort of checking this question, we found the following thing, that the beam comes in and creates very high frequency plasma waves. Once it creates these plasma waves can be seen as a radiation pressure. That's the radiation pressure that you exert in a plasma. When you exert a radiation pressure in a plasma, it can bunch ions. And it bunches ions, and so you have a decay situation where the primary plasma waves decay to some secondary plasma waves and ion density fluctuations. Once these waves decay faster than they are produced, there is no instability anymore. And since there are no very large amplitude waves here, the beam doesn't see many waves, it doesn't flatten out. And it decays down to some lower frequency waves, which can drag tails symmetric, like the ones, counter-streaming symmetric tails that have been observed up there, and some density fluctuations. To check this idea, we had a code, and we try to simulate this problem. Here I'm showing you the results of this simulation. The results of this simulation is the following. We had the waves, and they are growing with a growth rate which is of the type of the growth rate you will expect in auroral beams below 1,000 kilometers. Is there any pointer? Here it is. Well, these are the waves that are in phase with the beam, and they grow initially. If these waves stay there for a long time, they'll just splash the beam, so you will see a flat distribution. One of the things that we see is that these waves, when they reach a certain level, they sort of splash down and decay. However, this is the energy density of the high-frequency waves. This sort of keeps constant, so it gets transferred out into some other region where they do not interact in phase with the beam. And one of the things you see is that the total wave energy stays constant. So the beam doesn't lose any energy, doesn't slow down anymore. So you have stabilized the beam. Another thing that you see is these are the low frequency density fluctuations. They grow up and they stay constant. Once you have low frequency density fluctuations, they can produce anomalous resistivity. So you have the beam coming up, being stable, and producing anomalous resistivity. Once you produce anomalous resistivity, you can have constant electric fields. So if you had a beam, which is 100 eV initially, you can have an electric field who can accelerate the beam to 10 keV or 20 keV or 30 keV. So it's a self-accelerating process. If 100 eV electrons come into the magnetosphere, and they sort of form such a situation, you can create density fluctuations large enough to increase the voltage across, and these fast particles will continue accelerating. Since people would like to measure these things, we would like to show them the spectrum of the density fluctuations. This is the spectrum of the density fluctuations we see under these situations for 3 or 4 different times. This is the spectrum, delta n over n, as a function of the wavelength of k lambda d in terms of the Bayer length. You know, the presence of these density fluctuations creates an anomalous resistivity, although you might not have a situation where the current is unstable. The current is absolutely stable. You have a beam coming through, creates density fluctuation. It's like having an external source which modulates the ions, and you get this type of anomalous resistivity. And since Fred talked about some weird structures which he called spicons and things like that, I wanted to show you the results of the numerical simulation of how locally these structures will look, so that the people that are planning to measure them can look for them. This is what comes out of the code. This is the density fluctuations in X space, not K space that I showed you before. This is about 30 dBi lengths or something like that, 25 dBi lengths. Now, the presence of such things will slow down the electrons, the cold electrons, and also scatter the fast electrons. Well, I mean, that's all probably I can say. So that what? I'll tell you. The potential is fits exactly to this number. No, it fits to the number. You see, you have a density depression. You have to have a potential to force it, and that's it. That's the high frequency potential that keeps it. So, I would like to show several things like that, but I hope that experimentalists go and try to measure those things at some point.
Any comments? I suspected he would take your time, Akira. Why don't we take a maximum of 5 minutes, absolute, and then we go to George.
2 minutes, Frank. Can I write here, or?
You're not going to use it on my hand?
No.
Okay.
Just leave it. No, I don't want. Thank you for giving me 3 minutes. This field-aligned electric field that I have commented, I cannot write on here, can I? Was very rough, so I wanted to just give equations and so that you can evaluate how large potential variation can originate from dB/dt. Okay, so I just take the ordinary, it's not very nice, simple Cartesian coordinate and take z direction to be the background magnetic field, and x direction is in the direction where the irregularity or some kind of irregularity exists, and y is a direction in which the perturbed magnetic field, wave magnetic field, the time-varying magnetic field, dy. Okay, and this structure I'm talking about on the order of ion gyro radius. And it is easy to see that when the two magnetic fields oscillate within the ion gyro radius, ion cannot move with the magnetic field because E cross B drift is all mixed up, while the electron can still move with the magnetic field, and that sets up the charge separation. And therefore, that when the structure in the x direction is on the order of ion gyro radius, electric field along the magnetic field cannot be cancelled. And that gives you a simple Maxwell's equation of dB/dt is equal to Carly, that is proportional to dE of field-aligned electric field, and dx, which is just nothing but ion gyro radius. And of course, there's another term, dx over dz. One can show from the kinetic equation these two terms becomes comparable when you talk about ion gyro radius type variations. So actually, it's proportional to dEz. You can write down it's proportional to the whole thing. It's proportional to dEz dx, which is just Ez over ion gyro radius. So you can calculate Ez potential along the field line is equal to just integral of Ez dz, and this is nothing but integral of dby dt times rho I times dz. Okay, and dz dt is like alpha n speed, so this is roughly equal to alpha n speed times ion gyro radius times wave time varying magnetic field in a transverse direction magnitude. Okay, and this is a very simple formula you can take, and you can just take the number that you see in the tail. If you take a few gamma in amplitude of magnetic field, this actually, if you put in numerical values in the of the tail, this just becomes very simply by amplitude itself given in gamma unit kilovolts. And that's so if you have 10 gamma variation, you have 10 kilovolt along the field line, and that's also give a very nice number.
If there are no comments, are there? If not, I think we'll